Hello, I am Tim Holey, and this is the third session of our short course on advanced scientific computing producing better code. Focus of this session is on testing and the consequent principles of design that adopting a test-centric mindset can help you figure out more quickly if you don't already practice these. So we're going to be talking about testing, how this contributes to the reliability of software, and how, maybe somewhat surprisingly, it can also help you improve the design of your code. We're going to talk about the actual mechanics of writing tests, and then we're going to talk at the end about one last topic: how do you know how well tested something is? There are numerous reasons to be concerned about the quality of code. I'm a scientist, and this course is targeted to scientists, although I think the principles hopefully should apply far more broadly than that. Science is certainly increasingly reliant on computation all the time. And the problem is that while there are fairly widely established standards about experimental science in terms of what kinds of steps are necessary in order to prove a case, or just look sufficiently carefully that you know what background work has been done, there really aren't very widely agreed upon standards for how the analysis part, the code part of a project should be documented and what sorts of metrics the testing needs to satisfy. And the scary thing about this is that it's widely known that code is prone to errors. And so some studies of this have suggested that, oftentimes several percent of the lines of code in a project may actually have latent bugs in them. And this applies even in many cases to the sort of so-called finished code as part of a project, not just the sort of in progress code. It's also, though, widely agreed upon that you can do a lot to reduce this error rate considerably, and that, depending upon how much effort you're willing to invest in this, you may be able to get it down by one or more orders of magnitude. And while this may not protect you against the possibility of any kind of error, it certainly diminishes the risk of serious error or just simply personal embarrassment. So, testing is key, I think, to reducing the number of errors in your code. And testing often falls in two broad categories: static testing, and that is that code that just simply looks at the actual source code itself and tries to intuit the presence of errors. And in Julia, there are a couple of packages that have capabilities in this kind of domain. The more relevant form of testing for today's lecture is so-called dynamic testing, and this is just where you run the code and check that it's giving you the results that you have reason to expect. And one of the things that I found surprising is that testing, as I learned more about it, can not only reduce bugs, but it can actually give you a better development process that results in better outcomes. So I'm going to go over that. And hopefully, I don't think I'll convince you of that today if you're not already convinced of that, but I will hopefully at least encourage you to give it a try, and you can find out through your own experience whether new ways of doing things produce better outcomes for you. I do want to tell you a little bit of sort of motivation of why you should consider doing this. And I want to give credit to Evan Dorn, who made a YouTube video that was my sort of official introduction to this topic, although I'd been learning from peers for some time by that point. And he pointed out in his video that one of the almost threats to high quality code is the fact that many coders are really smart and they can juggle a lot in their head. And because of that, they're often tempted to just simply sit down and start typing to implement a project, basically. And this is, of course, a lot like a building engineer who says, just give me the bricks and I'll start construction right away. And many of us would say that's kind of silly, right? We know that building a building, there are high costs if that goes wrong. And it's worth spending some time planning in advance to ensure a good outcome. Well, developing software is expensive too. It's expensive both in terms of your time, and if you're in the business of providing resources for programmers, it's expensive in terms of money. And so there are just as good reasons to imagine needing some kind of planning for software development as there might be for building a building. Now, software development does not come with a crystal ball. I don't want to claim that careful planning can always work or that you may not be surprised by something. That happens all the time, right? But what that means then in part is that the part of the work that you do in planning should, you would hope, be leveraged in a way that gives you a long-term value, even if it ends up leading you in a direction in terms of your implementation of things that you'd never expect. And testing is almost ideally suited to do that. You can often get by. Part of the reason that smart people do this is because they can often get by. It works, because they can juggle a lot in their heads. But the value of testing, and I think one of the reasons why I don't think I can convince you today, if you're not already adopting these packages or these processes, I don't think I can convince you that you have to start testing your code more carefully, because in a lecture like this, I can't do a complex demo, and the value of testing rises with increasing complexity in the project. So the only thing I think that I can do today is to tell you some of my own personal observations that I've seen over time, and at least demonstrate how you go about the process of writing your code in conjunction with your tests. And then hopefully you'll give these ideas a try and use them to write better code. So for me, one of the origins of my interest in testing grew out of an experience that was a very painful, hard lesson. And that is that for my group, I was in the habit of writing some of the more sort of difficult algorithmic code. And I would develop this very carefully. I would pass in fake inputs where I knew what kind of outcomes to expect. I might step through it line by line in the debugger and look at the current state of the program at each state. And only after going through this, sometimes maybe for days of analysis and fixing bugs and things like that, would I feel confident enough to sort of push this out. What happened for a few projects was, well, what happened for more than a few projects, I would have sometimes get a bug report. And occasionally what happened was very unfortunate. I would get the bug report. I'd say, oh yeah, that's a bug. I'm going to fix it. I would go to fix it. I would push the fix out. And then very shortly thereafter, I'd get a new bug report of a bug we'd never had before. And that was because my fix of the first bug triggered a new second bug. And then I would flail around trying to get to a state where I didn't have either bug, and I might introduce a third bug. And there were times when I got to the point where I basically had to either freeze a bit of code and declare that we were never going to be able to develop a better version than this, or re-implement something entirely from scratch because I was just lost, right? And this was because some of these were fairly complicated projects. But more importantly, I do much more complicated things now than that, much more complicated, and I do them easily and successfully. And the main reason why is because I've adopted a test-centric framework in my own development processes. So the key thing that I was missing before for at least introducing this idea is that all the problem that I had before was that all of that work that I did in analyzing my code, stepping through it in debugger, all that kind of stuff, none of that was reproducible without me actually just going through the exact same process manually again. I didn't save any reproducible variant or version of that work. And that's often what tests are. They are essentially a set of tests that your code must pass, and you can rerun them. If this is an automated test suite, you can rerun it and see how well your tests do. And so these having tests has many advantages. They document what you expect your code to do. They help you validate your initial implementation is working. That's useful to you. That might also be useful to other people. Now it's visible. The work that you did to validate your code initially is visible. But the most important thing I think that having a test suite gives you is that it actually frees you up. It lets you make improvements to the code later. And you, by and large, especially if you've written really good tests, you really don't have to fear that you'll trigger new bugs, because you'll discover it instantly if you run your tests and suddenly things start failing that used to work. And this gives you essentially protection against the kind of failure model that I experienced before I learned the value of testing. So all of these are really good reasons to have tests. There are also good reasons to write tests, and I'll get to those in just a minute. But I do want to begin with a very quick demo of how this works and show you in Julia how you go about this process. And I'm going to use a development workflow that will become more obvious about why I'm doing it this way in a minute. So I'm going to create a package, and in your previous homework you learned about this package templates package. I'm not going to explain it right now. This is just a dummy project, so I'm going to create a package in a temporary directory, and I'm going to create something which is an analog of something that you also saw in your previous homework, and that is that you use the module docstrings package to harvest the first sentences of a bunch of different functions in a package to provide an overall summary of what that package did. And so what I'm going to do here is start on the process of implementing a first sentence extractor from text. Okay, so I'm going to create a package. I'm going to call it first sentence, and Julia is setting this thing up right now. And then I'm going to open it up in VS Code, and we're going to start developing this package. And you may know, right, we talked about the structure of packages and how they have several important directories. There's the overall, let's see here, this is an old one. Yeah. Here is the source code. Of course, it's a stub. It was created by package templates. And here is the directory that holds all of the tests. And so it loads the package, it loads Julia's test suite, and then you start writing your tests inside of these test sets here. So I'm going to do something which, if you've not ever followed this before, may seem strange. And that is I'm going to write the tests first. And the reason to write the tests first, I'll tell you in a little while, but it gives you several benefits. So we're going to try that. If I want to, first thing you might always do in computing is you try hello world. So if I pass a string that is hello world, then I imagine that I might have a function which I'm going to call first sentence, and I can pass in a string. And in this case, this string only has one sentence, and so I want it to actually just return the string back. And so I'm going to test that this is true, okay? And so I'm going to actually execute this. So I'm going to go into the test directory. There's nothing complex about my environment I have to set up, so I'm just going to include it. And I run my test suite, and unsurprisingly, it fails. Unsurprising, because I actually haven't written any code at all yet, right? Let's check actually where and why it failed. So here, if I right click or control click on this, takes me to the line that failed, line 6. Sure enough, that's a place where it's reasonable for it to fail. And it's failing because first sentence isn't defined. That totally makes sense. Because we've gotten good recently at using Git, I'm actually going to take the time. This is actually an achievement, even if it's not passing yet. And so I'm going to take a chance to make a commit, add a one sentence test, and voila. So now I've actually saved for posterity this work that I've done creating my test suite. Now my mission is to make the tests pass, right? So I could be in the situation because somebody reported a bug or I discovered one and I created a test that captured that bug. But even when I'm hammering out the initial design of the package, this gives me a chance to start specifying what I want my code to do and what kind of results it should produce. So now I'm going to actually create my first implementation of first sentence. And I know that I can actually get away with a really pretty trivial implementation, right? And let's try the very dumbest thing I could possibly get away with. I'm just going to have it return the string, right? So export first sentence. Now, those of you who are observant will notice this is a pretty bad implementation of a first sentence, extractor, and that's true. So I'm running a package called revise, and so my code was updating, and that brief delay was for revise to compile itself. Now, from henceforth, it'll be fast to do that. And now that I've implemented first sentence, my test passed. You might say, hooray. You might also say that's a bit alarming because it's such a trivial implementation, it's obviously wrong. Well, the problem is we haven't written enough tests to really exercise the functionality of this to prove, to be able to detect a failure mode, right? And so I'm going to commit my fix. So add trivial implementation. And so now I have a couple commits in my project. Let's go back and let's be a little more demanding, right? Let's give ourselves the chance to detect problems in our implementation before they arise in real world, right? So let's try a 2-sentence sentence. So hello class, we are covering testing. Okay, and then for this case, I'm still going to test my first sentence function. And I'm going to, in this case, insist that it is just the first sentence. Hello class, and that's it. Okay, so now let's run my test suite. And it fails. Okay, so and here you can see it actually passes one of my tests, but it also fails one of my tests. Which one does it fail? Let's right click on it here, and it fails the second test, unsurprisingly, right? And here you can see the output. Here it returned the whole string on the left, so there, but the right hand side just is the value I'm comparing it to, and they're not equal to each other, hence it fails. Okay, I'm going to commit my test, add 2-sentence test. Again, I've done real work here, so it makes total sense. It runs properly, does what I expect. Let's get it committed. All right, so now we're going to redesign this function so that we can pass that new test. So it's going to be a little more complicated. So I'm going to use the long form of function declarations. And I know how to do this, right? So Julia has a lovely function called find first, and it's going to return an index. So I'm going to call that return value index, and it's find first. And I'm going to look for the first, well, let's look at our test. So there's a period that ends this first sentence. So I'm going to look for the first period in my string. Julia offers a really nice way of finding a single character. You could do it as a whole string, but if you're really looking for just a single character, the most efficient way you could do this is to create a function that returns true if you pass in a character that matches. So this essentially computes is character equal to dot to the period, and then that function will return true if the next character is a period. It will iterate through the characters in the string and return the index position. Okay, and then what I'm going to do is I'm just going to return the string up to and including that period. And so I'm going to go from the first index to the position of the period, return that value, and voila, this should work. Okay, let's try it out. So I run my tests, and I'm still getting one pass and one error. What happened? Well, where did it fail? Very interestingly, it actually failed in my first test, right? And in fact, the passing test is now the second one. So I passed this test probably, and you could verify that directly yourself if you wanted. It's true, and you can infer it clearly from the output. And it's actually the first test that fails. Why did it fail? Well, there was a method error, meaning it couldn't find a method. And what this is trying to do is construct a range, a colon, between an integer and nothing. Well, let's look at why. Well, the problem is, if we look at that first test, there is no period in that sentence, in that string. And so find first in that case returns nothing. When it returns nothing, then this indexing operation fails. And that's the origin of the problem. But you can see we've tried to create a better implementation than we started with. And it was actually one of my old tests that caught the error. My new test passed. The thing I had foremost in my mind as I was modifying this function worked. Unsurprisingly, I was aiming my implementation at this new capability. But what I forgot was that an older capability that used to work no longer works. So how might we go about fixing this? We have to do better. And so rather than just comparing to a period, sentences can of course end in other characters. And so let's allow this to be any one of several. So I'm going to say if it's in a set of potential characters, and that set will include, of course, a period, but also an exclamation point and also a question mark. Okay, so this is the in operator. It's asking if whatever character you're testing is in the set of these three things here. And if that's true, then everything should be good. So let's try running our tests. And now we do it. And now they both pass. Hooray, we're in better shape. So I'm now going to commit my code in better form. So add a first sentence extraction. Okay, good. All right. So now, again, this is still very bare bones. I have very few tests. There's lots of ways this would fail. It might fail if I had passed an empty string that has no punctuation and even has no characters to it. You might want to throw an informative error in that message. I think that's actually a question where the design of this, we haven't fully fleshed that out. Our tests offer us an opportunity to flesh out what should happen in that case, and they document that behavior and make it sort of ironclad. There are lots of other cases where it would fail. Periods can occur, especially in Julia. First sentence as a module has in it a first sentence function. This dot is in the middle of something, and that will get detected by our implementation. So we might want to check that the next character is a space, for example, right? So there are many ways we can improve it, but the point is that as we make improvements, we continuously expand the test suite. I like to write the tests first when I'm, thinking carefully about that, and this is something then that make sure that I know my implementation moves forward as my test suite moves forward. Okay, so what I was just practicing was an approach to software development known as test-driven development. And in this process, you might add a test either because you're intending to make sure that your code can do something new, or maybe because you've gotten a bug report and you're trying to capture that bug in a test. You create the test, you watch the test fail. Only then, after you verified that the test fails and in the manner that you expect, do you write the code to try to fix it, and then you run the tests, hopefully verifying that they fix. Since you now know a lot about Git, you also know that you should make commits when you've achieved something new. I think it's valuable to make one commit after you create the test, another when you get the fix. But it's especially, you don't go beyond this point without making a commit. And the reason why is that very often when you first get something working, you reach there, it wasn't an entirely clean development process of getting there, and your code's a little bit messy. First thing you want to do is clean it up. The problem is if you don't make a Git commit, sometimes your attempt at a cleanup can actually break something that you had just worked very hard to get working. And so if you've made a Git commit, you can always go back and try your cleanup a second time without any risk that you've lost something that was once working and now have to painfully recreate, right? So Git's very much an advocate of yours in a cycle like this. So you essentially, continuously go through this cycle, and on each cycle, your code gets better, more comprehensive, more fully tested, etc. So what I want to say is, of course, it hopefully is obvious that this is a good way to increase the quality of your code. One of the things that often, not always, but often occurs is that the actual act of writing the test also helps you create better code. And the reason that happens is there are several of them. One of them is it gives you an opportunity to sort of exercise your code. You pretend we had this first sentence function, even though we haven't written it yet. It gives you a chance to test out your application programming interface, as it's sometimes called, API, before you actually have sat down to do the hard work of writing it. And you may not like what you see when you start looking at maybe a much longer, more extensive set of tests that you write right at the outset and say, that's pretty ugly and painful to use and awkward for the user. I don't like that. I'm going to redesign the API before I've written a lick of code. The other thing that, sort of writing tests often does for you is it helps you realize cases where you've written code that is just almost unmaintainable. The experience, I think, widely seen is that testable code often tends to be higher quality code than code that is difficult to write tests for. Let me show you an example of what I mean. This is a function here. It takes numerous inputs that are required positional arguments, and then it also has a number of keyword arguments that you can use to sort of modify the behavior of the overall function. In some cases, you might be able to supply default values for all of these options right here in the signature, in which case, maybe this is more justifiable. But in more complicated cases, the value of these default options might depend in complicated ways in the combination of all other options. So you might have to write a substantial amount of code that actually just simply to set the options, right? And so then finally, once you're through that process, then the real computation starts. Now, this is actually extremely hard code to test well. And the reason why is partly because the actual ability to inject data into the code is very far removed due to all of these preliminaries from the place where the real computation happens, right? And that leads to much greater difficulties in writing good tests for the code. And among languages that are widely used in scientific computing, I would actually call out MATLAB as being particularly bad about actually actively encouraging people to adopt designs like this, in part because of their limitation of only having one callable function per file. But I wouldn't let other languages entirely off the hook either, right? So a lot of the library functions in, for instance, Python seem to have an awfully large number of options. And if a function has 12 different options, and each of those can assume one of two values, that's 2 to the 12th potential combinations. Are you really going to write tests for 4,000 different possibilities? Maybe it happens sometimes. It's a lot of work to do so. And one of the nice things about Julia is that the actual language design itself circumvents that problem in many practical cases. Not always. Maybe you really do need all 12 of those options. But in many cases, the options only make sense in certain combinations. And what Julia allows you to do is to create dedicated methods to handle those special cases. And the code that follows the signature, which determines which method gets called, is often direct and simple. It doesn't have this long prelude before you get to the business part of the function. And it gives you an immediate handle, and one that doesn't have a lot of cruft associated with it before you get to the business part of your code. And so Julia, and if you try to call a combination with arguments that isn't supported by any of your methods, you get a method error, right? There is no way to run your code, which risks logical errors with combinations of inputs that don't make any sense. And again, it's up to you to decide what does and doesn't make sense. There is no universal answer to that question. But Julia has the language features that allow you to easily enforce a very sparse set of allowable combinations of arguments among a gargantuan space of potential argument combinations, and that really improves the ability to write clean code that is also extremely well tested. I want to at least sort of sketch another example of how the process of thinking about testability can help you improve your design. And this example may be obvious to many of you, but may be illuminating to some others of you. And this comes up a lot, I think, in my kind of work and maybe many of the rest of yours. And that is, let's say you have a big directory full of different files. They each have data in them. But for a variety of reasons, maybe not necessarily one that has HDF5, such a flexible format that can code a lot of things in the file. But some formats don't really let you encode a lot of meaning into the conditions under which a given data file was generated. And so what often happens is that people use the file name to encode, to endow meaning to the sort of context in which this particular file arose, basically. And let's say that your task is to take a whole collection of such outputs and draw overall conclusions, right? And so you might have several different steps to this. You may need to load the data, maybe from all the files, maybe you want files one at a time. You need to do some kind of analysis, and then you might plot the results, right? And so if you were to write one giant function that did all of this work, I hope it's probably pretty quickly obvious to you that you've ended up with a completely untestable mess, right? Because the only way you can really test the outcome is to run the code and look at the plots, right? I mean, you can test whether plots are what you expect, but that's a very tricky business, and just slight changes in your data are going to change your plots in ways that may make your tests very fragile, right? So probably most of you who are watching this would not, would know that that's problematic, right? A much better way to do it, of course, is to split out portions into testable pieces. And the most obvious portion that's testable would be this analysis stage. So you might create different analysis functions. Say some analyses may only take one file at a time, and other analyses may do a comparison between files. And you may want to then check essentially that these analyses give you the expected output. Well, in the process of thinking about this in practice, if you have a very good defensive programming mindset, a scary thought might occur to you. When you're writing the tests, the outcome, the output that this function should return to you depends not only on the contents of the file, and that's nominally why you're passing in the file name as an argument so that this can load the data, which it then needs to do the analysis. But remember that we've also encoded important context into the file name itself. And the question that might arise if you were a healthily paranoid defensive programmer is, what if I just change something about the representation? Maybe not even the actual sort of meaning I intended to convey, but just a stupid detail about my representation in that file name, and that triggered some kind of bug. Would I get a different answer? And an example of that might be, you may notice if you look back at some of these file names, my early file names for this A parameter here, they all happen to be integers right before the file extension. Then at a certain point, I started testing, fractional values here. And so now this needs to be a floating point number. And if I've integrated my parsing code that extracts meaning from these file names into, my analysis functions, if that code assumes that it's an integer and stops after the 7, it might do that analysis assuming that A has a value of 7 when actually it had a value of 7.5. Whether that's a serious bug or just a small sort of almost inconsequential change, depends on what kind of analysis you're doing. But this is the kind of situation where you've essentially, set yourself up where there are multiple ways your code can fail. It can fail to do the analysis part properly, but it can also fail to extract the context properly. And that's a bad circumstance. There are some sort of aphorisms that you'll find in any set of advice about good code design. And the example I just gave you violates several of them. One of them is the so-called single responsibility principle, that code should just do one thing. So if you had this guideline in mind, you probably wouldn't make that kind of error. Another one that might save you in this kind of situation is another important aphorism called don't repeat yourself, or DRY. And if you had, for example, essentially copy and pasted your parsing code from analysis 1, then when you started analysis 2, you just pasted the same bit of code. Now you have at least 2 places you have to fix the bug. And maybe you don't remember to do that when you're in the heat of debugging something, right? So either of these aphorisms or both could certainly save you. There are also, I should acknowledge, some other good aphorisms out there. And on your homework, I have a link to a site that has even more of them than this. But it's important to realize that you could also arrive at this place through thinking about just how testable is your function and how many different combinations of inputs are going to be necessary in order to really provide for robust testing. And that alone can guide you to the, developing these principles and living these principles on its own. So what would make the way I might tackle a problem like this is I might create a structure whose whole purpose is to encode the results of parsing these file names. And so then I might have a constructor for this structure that takes the string of a file name in and then extracts all of the different characteristics I want to extract. And a key thing is that it would do the full transformation on those inputs. It would put them into the most useful form for consumption by downstream code. So for example, rather than encoding the date portion of the file name as a string, that's vulnerable to problems. If I'm sorting in order, I don't usually want to sort dates in alphabetical order because maybe the 8th month of August would look like it came after the 10th month because the 1 in 10 is alphabetically before the 8. That's not good. So I'm going to take it all the way to a type in Julia called a date, when that's a standardized date format. And if you sort in temporal order there, this is robust against those kinds of problems and so forth. Every place where I want to extract meaning, I ensure that this kind of thing here is the most usable representation I can come up with. And then I can test it. I can test my constructor, give it there's no data attached. These aren't real files. These are just strings. But I'm testing to see whether my extraction of meaning from these strings, the context that I need to get out of them, is working properly. And once this is working properly, I make git commits, and then I move on to the task of actually writing the analysis code. I've separated this out into 2 separate pieces. I've established a beachhead on one of them. I know that portion of my code is working well, or I can detect problems in it separately if they do arise, okay? So, and again, the sort of strict test-driven development would say that you should write the tests, and that's great. I recommend doing that. But the most important thing is to just develop a test-centric mindset as you create your code. Okay. So, hopefully by this point you have a clear picture of the role of testing. There are negatives to it. It does take time to write tests. Those are lines of code and you have to type them. So they generally take time to create. And it can feel very unrewarding and bureaucratic and annoying if you wait until after all your code is finished and then start writing your tests, because you're not getting any value from that process because you already have something that seems to be working, right? But the problem is that you're going through a long period of time while you have no net under you, no safety net to catch your mistakes. And then you're trying to build that net after the building construction is done, right? And that can end up costing you a lot of time. As much time as it can take to write tests, usually writing bad code and then having to fix it can take even longer. And so the time you invest here can save you a lot of time here. And having this down as a good process not only makes it less of an annoyance, it really feels like you're benefiting yourself, because you get very good at the process of quickly writing a good set of tests. This helps you think through your design clearly, helps you head off some mistakes, not all mistakes, but some mistakes before they happen. Okay. So, I also do want to acknowledge that there are limits to all of this, right? There are things out there that are so hard to test, it might not be worth your time, right? And I think anyone who's written code for a while has encountered those situations. I have sections of my code that I've just declared are going to remain untested because they're just so much of a pain to test, right? I also don't write tests for really trivial things, right? I don't check that adding 1 to a number increments it by 1. I assume that's the job of whoever created and is testing the numbers handling suite. And if I'm creating my own number type, yes, I'll test this. But if I'm not doing that, I assume that's been done elsewhere. It's also fine to play around, but when you start deciding some of this is worthy of keeping, that's the moment where you transition to making sure that you have those tests. A final thing, and I find this to be a common thing, if I'm starting from a bug report, either that I've discovered on my own or someone had sent to me, sometimes that bug report starts out really gargantuan and complex. It doesn't make a good test in and of itself, but it's also a sufficiently complicated circumstance that I can't write just off the top of my head a simple minimal working example that triggers the same bug. And so I might not need to dive into debugging the problem first. And in some cases, I can't even be sure that I found the essence of the bug until I fix it. That's fine. That's a normal development work process. But you should still think about doing things like, once you convince yourself you understand the test, instantly write a minimal working example that captures the essence of that test. Make sure that your test fails on the old code, and you with git and git stash and making commits and the revise package. That's actually, Julia offers a very easy workflow for committing your tests, stashing your changes, and then making sure your tests fail, popping the stash, and then rerunning your tests and making sure they pass and making another commit. So that's actually a very easy, pain-free workflow that also allows you to make sure that your tests are really capturing what you think they are. So there are limitations to testing, and I would never encourage you to go to more work to test than any value that your code derives in the end from it. That's the overall goal, is to get to good code no matter how you get it. I want to cover, one other major topic, and that is that, coding is often a collaborative process. And while you may hopefully have a good sense of how well tested your own code is, if you're starting to join a new project or work with someone else, you may want to get a quick sense of how thoroughly tested their code is, right? And I often, now that I've gotten used to a very sort of test-centered way of developing my code, writing code, doing coding without those tests underneath me, again, feels like programming without a net, basically, right? And before I do something really dangerous where I might risk breaking something for myself or for many other people, I might wish I had that net. So in some circumstances, it makes sense to actually help fix that first, or at least you should understand what you're getting yourself into. And to avoid embarrassing anyone, let me show you two sort of different extreme ends of what this might look like. So let's first look at a reasonably good package that is kind of is fairly well tested. This is both of these packages are actually focused on a topic we'll cover in future sessions, that is measuring and visualizing performance bottlenecks in your code. And so what you can see for this package here is a set of badges. And the first of these badges really sort of focus on documentation and whether the tests are passing. This last badge here is a measure of what's called code coverage. And you can see it's giving a single number of 91%. And so what that means is that 91% approximately of the lines of code in my package are triggered by running the test suite. If you click on that badge, you can get taken to a website that allows you to visualize some aspects of your code coverage. And if you can navigate into the source folder where all the source code for this package is. And I might click on a file, for example. And what you can see, well, sort of comments and doc strings don't really count. And so they're shown in gray here. Type definitions don't, but this is marked in green because the constructor runs. But then as you go through, you start looking, and at lines of code that can actually run, you can see many of them are marked in green. That means that one or more of the tests in my package exercised that line of code. It executed in the course of running my tests. But if you scroll down far enough here, you get to a red line, and that suggests that this line of code was not run in any of our tests. And what that means is that I failed to come up with a combination of inputs that triggered this particular condition, which would have caused this line to run. So this is a vulnerability, if you will, in my code. I don't actually really know that this line works properly, right? As a consequence of my test suites. If I edited this line and put a typo in, I might not discover it until a user reported a bug, right? But overall, you can see the large majority of lines in this file are green, and that suggests reasonably good coverage. So there is a net under you. If you were to start collaborating on this project, you could feel pretty confident that you wouldn't break anything, hopefully, right? Just because the line runs doesn't mean that it's thoroughly tested with all possible inputs, but at least it's better than not having it run, that's for sure. I want to now show you the other package here, and you can see here that the coverage analysis on this package is far, far worse, right? And there actually is a reason for it, and it's the reason these are two separate packages. The first one is more sort of algorithmic for analyzing and constructing data structures that represent performance data, and this package is actually a graphical user interface for interacting with it. And so when you click on the analysis of the coverage for this particular package here, and you click on the individual source files, and you start taking a look, they're much, much less well covered. There are a few examples here. Here I forgot to check an error condition. I should have done that, didn't do it. But you start seeing some of the really big failures of test coverage down here. So what that means is that these would be much riskier portions of the code to make edits to. You wouldn't have automated guarantees that your changes didn't break something. Now there is a reason for that. And in this case, this is because these are lines that run contingent upon user interaction, moving a mouse or clicking on buttons and stuff like that, right? And so these are much, much harder to test. But I'll show you in a moment that had I known at the time I first wrote this what I know now, there are ways that I could have set up the testing even for some of this. And I'll show you that in another moment. So, but the most important lesson I want to take from this understanding of the tools that are available to you to analyze coverage is that you have a way of understanding the test coverage and therefore some sense at least of how thoroughly tested a package is. And if you do find that there's an important package that you really think is worth your time, but you need to make extensions to it, and you discover that it's poorly tested, one of the things I've sometimes done is I get together with the author of that package online. I talk about my situation and then propose that what we do is we first spend some time working together to improve the coverage. I might do a lot of the groundwork, but I might need input from the package author to sort of specify things that are not fully specified, by, like, is this the way this is supposed to be working, or is this a bug, right? You may have questions like that. Once I've essentially assembled the net, I then feel much more confident about making the kinds of deep changes I might need in this package in order for it to really fill my particular needs, right? And so sometimes this is a step that, as painful as it can be very worthwhile. The last thing I want to mention is two special topics. One of them is just testing for errors and warnings and things like broken tests. So that I encourage you to read the documentation in Julia's test library. In addition to testing for working things, as I did in my very brief demo, you can also test that code produces errors of the types that you expect or messages that you expect. There are ways to test that certain messages are sent back to the user, so to warn them of something, but maybe not throw an error. It's also okay sometimes to write tests that fail. And you may say, okay, I really want this to be true, but that is going to take me a long time to implement. I kind of need to move on, right? Never fear, still write the test and capture what you want to be true, but then mark it as a broken test. This then essentially becomes part of your or your collaborators' to-do list, right? Eventually, we want to get this thing working. This is our intention of where we are headed. It's not there yet. We've clearly indicated what we want to happen. We've also clearly indicated that it isn't working yet, right? And so this is better than not having that test, okay? The last topic that I want to mention here in these special topics is that it actually is possible sometimes to test things that you might think would be untestable. And this example is for these graphical user interfaces. So one of the really elegant things, I learned when I started working with the Julia community was of the concept of observable variables, sometimes called reactive variables or signal slots. And what these are variables where you can set a value, but you can also create functions that run when the value of that variable changes. And so I'm going to create one of these variables here and give it a value of 3. This returned to the actual function that I defined to run when it does that. So let me see. So since I created it to have a value of 3, let's just check that that's true. Sure enough, it has a value of 3. If I set a new value for it, you can see that the function runs, right? So it detected that I updated the value of the function of the variable and then ran the dependent functions. This might be called a callback under some circumstances. And if I then look at the value that's inside of the observable, you can see that it has been updated. And I can do this over and over again. I can set a new value, and the function runs each time I set a new value, and that so the value gets encoded, but it also runs whatever functions I've set to run on updates. And what this does is this gives you a way to decouple the graphical aspects of your code from the logical parts of your code. The way that you go about doing this is that the user interaction, all the widgets on your screen, they do nothing but inject values into a set of observables that you have already set up, right? So if you click on a button, it might change the value of it might just put true into a Boolean variable or something like that, right? And simply by stashing a new value in it, you can then run all of the functions that should run as a consequence of setting a new value for that observable. And so at that point, then all of your logical portion of your program code depends only on the observables and is completely divorced from the graphical, the widget toolkit, or whatever else you're using to actually manage the on-screen interaction with the user. And this gives you the opportunity to test that logical portion by setting up identical observables, maybe through your package code itself, but passing the observables back out to the test suite, and then injecting new values from the tests and seeing what happens to other dependent internal variables in the code. Okay, so you even can test the core, most difficult, most important parts of the logic of a heavily interactive package using techniques like this. So in summary, we've talked today a lot about testing. In my view, it's really an integral part of software development and really essential to producing high quality code. It's most satisfying if you write your tests in conjunction with the code itself, because it feels like you're helping yourself as you're helping your eventual users. And so if you use it as a systematic process, it goes from being a painful, bureaucratic annoyance into an ally of yours in creating great code. And in circumstances where you may not know through your own personal history, or you may just want to check and see how you're doing, you can use tools like coverage analysis to at least help sort of get a big overview of where the test situation is in a particular package. With that, I will close. Thank you very much for your attention, and we'll see you in the next session.